Hello, my name is Medeina Maciukenaite. I'm a master's student of environmental organization and I'm studying in Vytautas Magnus University and I'm working as chemical technology specialist in Lithuanian Energy Institute. And today I'm very pleased to be included in this conference and to present my research about sustainable catalytic potential of mugwort biochar. So firstly, why do we need these type of materials and why do they matter? So environmental pollution caused by heavy metals has become one of the most serious global environmental problems due to rapid industrialization, urbanization, mining, metal processing, textile production, and agricultural activities. Unlike many organic pollutants, heavy metals are non-biodegradable, persistent, toxic, and capable of accumulating in living organisms. Among various water treatment technologies, adsorption has attracted considerable attention because of its simplicity, cost-effectiveness, high efficiency, and operational flexibility. Activated carbon is traditionally considered one of the most effective adsorbents for the removal of heavy metals and, of course, organic contaminants due to its highly porous structure and large specific surface area. However, the high production and regeneration cost of commercial activated carbon limit its widespread application. Consequently, increasing research efforts have focused on developing sustainable, low-cost, and environmentally friendly alternative adsorbents derived from biomass materials. Biochar has emerged as a promising material for environmental remediation application. So what is biochar? Biochar is a carbon-rich solid material produced through the thermochemical conversion of biomass under oxygen-limited conditions, typically by pyrolysis. A wide range of biomass feedstocks can be used for biochar production, including agricultural residues, wood waste, food waste, and other lignocellulosic materials. The physicochemical properties of biochar strongly depend on the type of biomass, pyrolysis temperature, heating rate, residence time, and activation methods used during the preparation. Biochar possesses several beneficial characteristics such as I mentioned, porous structure, surface functional groups, ion exchange capacity, mineral content, and relatively large surface area, and all these properties make it suitable for pollutant adsorption. Although raw biochar demonstrates promising adsorption properties, its adsorption capacity may still be lower compared to commercial activated carbon. Therefore, different physical and chemical activation methods are often applied to improve its surface characteristics and absorption efficiency, of course. Activated biocarbon is produced through additional activation processes that enhance pore development, surface area, and the number of active adsorption sites. Activation can be performed using physical methods such as steam or carbon dioxide treatment or chemical agents, including phosphoric acid, potassium hydroxide, zinc fluoride, and other activating compounds. So the purpose of my research is to demonstrate the potential of mugwort as a biochar catalyst, and for clarification, in this research I had to analyze obtained biochar and activated biocarbon properties and of course evaluate if these materials could be suitable for adsorption. So let's jump to the methods, what I used. So to achieve porous structure and gain the materials without compounds which could disrupt the effectiveness, chemical activation with 5, 50, and 25% of phosphoric acid solutions were employed. Then thermal activation was utilized of treated materials under nitrogen atmosphere at 850 Celsius degree to achieve unveiled pores. Obtained biocarbon was analyzed using scanning electron microscopy coupled with energy dispersive spectroscopy and this equipment analyzed the surface morphology and elemental composition. X-ray diffraction analysis was conducted to investigate the crystalline structure and composition, and I used also FTIR, Fourier transform infrared spectroscopy, and it was performed to identify the functional groups present on the surface. So let's jump to the results, and first what I want to discuss about is ADAS results, and it showed that the more concentrated phosphoric acid was utilized, the less impurities in the materials formed. So in every sample, carbon was the one who occupied the biggest part of the materials, but additionally, with 5% of acid, calcium, phosphorus, lithium, potassium, and aluminum were noticed. Meanwhile, materials activated with 25% of acid were left only with carbon, oxygen, and just less than 1% of phosphorus. A tendency was observed indicating that increasing the phosphoric acid concentration during the activation process resulted in a lower occurrence and diversity of detectable elements in the materials. This phenomenon may be associated with the enhanced removal of inorganic impurities and volatile compounds during chemical activation and also during thermal treatment. Higher phosphoric acid concentrations likely promoted more intensive decomposition of the original biomass structure and facilitated the elimination of mineral components, leading to a poorer carbon-rich material and, of course, with reduced elemental complexity. Some analysis confirmed that as the phosphorus acid concentration increases, the more and smaller pores were unveiled. The activation process enhanced more pore formation and increased the overall porosity of the activated biocarbon. And these properties may improve adsorption performance due to the greater availability of active surface sites. However, at higher phosphoric acid concentrations, the material structure became noticeably more irregular and disordered. Excessive chemical activation likely caused partial destruction and fragmentation of the carbon, and it resulted in a heterogeneous and less structurally uniform material. FTIR analysis confirmed chemical bonds between oxygen, hydrogen, carbon, and phosphorus. It indicates that the bonds are attributed to hydroxyl, carbonyl, aromatic, aliphatic, phosphoryl, and phosphate ester groups. Materials achieved with 5% of acid showed bigger peaks, which indicates stronger adsorption. Of course, it reflected ADS results where highest amount of phosphorus was found in the sample with the same 5% of phosphorus acid. It was a very interesting notice because it can be explained that this sample was the one with minimum amount of washing because with 5% of phosphoric acid was a weak acid. According to XRD analysis, carbon was identified in all samples, and this indicates that the carbonization process was successfully achieved under all preparation conditions. Additionally, at 5% of phosphorus acid treatment, calcium carbonate was detected. The presence of calcium may be associated with naturally occurring mineral components in the raw biomass material that remained after the pyrolysis process. Furthermore, at 25%, sodium phosphorus nitride was formed, and the formation of these phases suggests that higher phosphoric acid concentrations promoted more complex chemical transformations and interactions between inorganic elements during thermal treatment. So, to conclude my research, I would like to say that mugwort demonstrates secure potential as a sustainable catalyst for green synthesis, and mugwort biochar chemical composition and physiochemical properties provide a sustainable alternative replacing toxic metal catalysts for greener synthesis. So, Thank you for your attention, and I'm waiting for your questions in the Q&A session.